Hello, it's dumplet here. Here's an item on geometry. Given triangle ABC with the figure on the left, we have the following ratios. BE is to EC is 1, AC is to CF is 3. Find the measure of angle DEF. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Alright, so we can make some primary observations here. Well, we have a nice given. We have the two 30-degree angles and a 60-degree angle over here. So we can try to make some observations here that, okay, well, AD is equal to DC because, well, triangle ADC over here is an equilateral triangle. And, well, coincidentally, 60 degrees over here is twice of 30 degrees, so maybe we'll be able to use that. And, well, 30 degrees and 60 degrees, they're pretty nice angles, so we might be able to use some trigonometry to form some maybe ratios to kind of maybe incorporate the ratios given with the trigonometric ratios in, for example, a 30, 60, 90 triangle. So, well, let's try to use the angles first. The fact that 60 is twice of 30. Now, we can exploit this fact by using the angle bisector, and that's a very typical technique. So let's try to bisect this 60-degree angle. So let's just have point G on AC. And I have the following claim. I claim that quadrilateral ABDG is cyclic. Alright, now this is actually pretty trivial. So let's just say G is on AC such that BG bisects angle ABD. Oh, sorry, angle ABD over here. ABD. So ABG and GBD would both be equal to 30 degrees, obviously. And since we're given that, well, CAD, which is the same as GAD, that's 30 degrees. So these two angles are both 30 degrees. Therefore, ABDG is going to be a cyclic quadrilateral. Now we can also note that, well, because of the cyclic quadrilateral condition now, we have this angle to be 30. That's going to make triangle ADG here to be 30 as well. Now we'll be able to use this later once we incorporate some of the ratios, because we will be having a lot of 30, 60, 90 triangles because of the fact that we have the 30-degree given and a 60-degree given. But the other reason is that there are nice points, D and E, that we haven't used that much. So let us try to use the fact that D and E are pretty nice points. Well, E is a midpoint, and the other one, D, well, it is the vertex of an isosceles triangle. So if I'm going to draw a perpendicular line to AC, let's just call it M for now, DM would be perpendicular to AC. And since triangle ADC is an isosceles one, M will be the midpoint of AC as well. Now, here I have the next claim. G is the other trisection point. Again, it might not be obvious at first sight, but based from my drawing over here, that's the first thing I noticed actually. It might be possible. Again, these are just claims, but fortunately for this case, it's going to be a true statement. So let us try to prove why G is going to be the other trisection point. Now, the motivation behind the trisection point is that, well, AC is to FC, it's 3 is to 1, or there's 3 in the given. So that's going to give us that AF is to FC, it's 2 is to 1. So we're interested in the other trisection point, and G here seems to be a very good candidate. And, well, in my case, I've actually found it to be true, and here's why. So here's where the trigonometric ratios will come into play. Now, let us draw DG again, because we're going to use the fact that ADG here is 30 degrees. And with this, we can already kind of see that AG and GD, they are the same. But let us try to draw out the other angles as well. Now, since M is a perpendicular angle over here, M is the point of intersection between DM and AC, which are perpendicular. That's going to be 90 degrees. Now, with this MDC, since this angle is 30 degrees, MDC over here must be 60 degrees. All right, so that's one. Now, the next thing that we can find is M is the midpoint now, so MF is to FC, that's going to be 1:2. Now let us try to, without loss of generality, assign a value for FC, so we can kind of make these ratios into actual lengths. So let's just say FC is 1. Again, without loss of generality, let's just say FC equals 1. Now if FC equals 1, then MF would be equal to 1/2. Now we can also get MF by thinking that, oh, FC is 1, so AC, the entire thing, must be 3 times of FC. So I'm going to write here, AC is going to be like 3. So MC, which is half of AC, MC must be equal to 3/2. Then, of course, 3/2 minus this FC, which is 1 already. We're going to get that MF here, it's going to be 1/2. So that's the other way to get MF. So I'm going to write this down here. MF is going to be equal to 1/2. Now we can use trigonometric ratios now, because MDC, triangle MDC over here, it's a 30, 60, 90 triangle. And we know that the side lengths in the 30, 60, 90 triangle are in the ratio 1:2, square root of 3 is to 2. So the sides opposite the 30, 60, 90 degree angles respectively. So with this, since we know that MC, which is opposite the 60 degree angle, it has length 3/2, so that's going to be 3/2. We know that DM, which is opposite the 30 degree angle, would be MC divided by square root of 3. And MC, which is 3/2, if I divide it by square root of 3, I'll get DM, which is going to be square root of 3 over 2. Alright, now by the same logic, we can use triangle ADM, which is a 30, 60, 90 degree triangle. And we can additionally use the fact that, well, ADM, it's going to be 60 because this angle is 30 degrees. And we know that ADG, based from the cyclic quadrilateral we got a while ago, that's 30 degrees. So this angle over here, GDM, it must be 30 degrees as well. Alright, so now that we have some of the lengths, DM being square root of 3 over 2, that's going to be in effect opposite this angle, which is 60 degrees. So we know that GM must be DM divided by square root of 3. So GM would be 1/2. And that's actually enough already to prove this claim. Now GM being 1/2, well, we can keep going. We can keep on going because GD is the hypotenuse of triangle GDM. Now GM is 1/2, so GD would be twice of 1/2. So GD here would be equal to 1. And since we have a 30 degree angle here, a 30 degree angle here, triangle AGD is an isosceles one. So I'll get that GD, which is 1, it's going to be the same as AG. So AG here would be equal to 1 as well. So AG being 1, now we know that GM is 1/2, so GF over here is going to be 1 as well. And there we have it. G must be the other trisection point because AG is 1, GF is 1, and FC is equal to 1. Alright, now again, they're not necessarily all lengths of 1, but at least we know that without loss of generality, if we assume FC to be 1, then we can prove that G is the other trisection point. Now there might be other ways to do this, but at least based from the given, having the nice special angle, it motivated us to kind of incorporate the length and ratios, the ratios given with the trigonometric ratios. Now with this finding, G and F are technically symmetrical now with respect to DM, since DM is a perpendicular, or bisector technically, of AC. So A and C are symmetrical with respect to line DM, G and F are symmetrical with respect to line DM. So I can kind of reflect GD over here across DM, and I'll get like DF. And all the angles that we got, it's going to apply. So 60 degree here, 60 degree here, and this must be 30 degrees as well. So all of these will apply, and interestingly, actually, we can find that triangle DGF, it's going to be an equilateral triangle. So more on this in a while. We have to make some further claims to kind of help us here. But there we go. We found that J is the other trisection point. Now, next, we didn't really use the fact that E is the midpoint of BC yet. I mean, yes, we kind of connected E and M here, but we didn't really use any properties related to the fact that, well, E is the midpoint. So let us try to do that. So I'm going to claim that BG is it's parallel to EF. Again, it might be obvious at first sight because of the figure, but it might not be obvious as well because we don't really have a nice figure with just our handwriting, sort of by hand. So, but in this case, BG parallel to EF might be a little bit obvious. Now, it's actually not that difficult to prove once we have the previous claim, G being the other trisection point. That's going to give us that GF and FC, they're the same. So GF is equal to FC, and we're already given that BE is the same as EC. So there we go, very simple proof. EF is going to be parallel to BG. So in effect, this EF is the midline of triangle BGC. Now, the other thing we can kind of use is that ME is also the midline of triangle ABC because, well, M is the midpoint of AC, E is the midpoint of BC, so the ME over here must be parallel to AB as well. So two pairs of parallel lines because of the midline. So there we go. Now, let us try to incorporate all of these into finding what triangle DEF is. Now, with these pairs of parallel lines, we're going to try to get what angle MEF is. So, well, triangle DEF, now that we have point M, it's technically angle MEF and angle DEM combined. So, well, the reason why I'm trying to get MEF is because, well, ME is parallel to AB, and there are a lot of angles here that we can kind of hope to incorporate with finding this angle. So I drew out some angles. So let's just say this angle, this yellow angle, is X. Now, since ME is parallel to AB, this angle must also be X. Now, I drew another angle Y, this red angle over here. And this angle over here must be Y as well because EF is parallel to BG. Now, since BG bisects angle ABC, as seen a while ago, XY and this 30-degree angle here form a triangle. And with the same reasoning, this X, this Y, and this blue angle, which is angle MEF, forms this triangle MEF. So with this reasoning, it can be seen that MEF must be equal to 30 degrees. Now with this 30 degrees actually, we can actually have a nice observation. Now recall that kind of equilateral triangle that we drew in the middle a while ago. If we put it back here, we can actually find that the EFM is cyclic. Actually not that difficult because we already have the angles that we need. Triangle GDF is an equilateral triangle. DM, which is technically in an altitude, the angle bisector as well, since it is equilateral. So MDF would be 30 degrees. So MDF would be 30 degrees, combining with the fact that MEF is 30 degrees, DEFM is cyclic. With this actually, we're already done because since it's cyclic, we know that opposite angles will add up to 180 degrees. So now recall that DM is the perpendicular bisector of AC. So, well, angle DMF, it's going to be equal to 90 degrees. Now, what's the angle opposite to angle DMF in quadrilateral DFM? It's this angle that we want, angle DEF. So, since angle DMF is 90 degrees, angle DEF must also be 90 degrees because 90 has a supplement of 90 degrees as well. So, there we have it. Angle DEF is equal to 90 degrees. So, in fact, actually, DE is going to be perpendicular to EF in this case. There we have it. So 90 is our final, and 90 degrees is our final answer. As a bonus, you can try to prove that, well, as D varies along DM, or line DM, so D doesn't have to be here, you can try to prove this question. D is on any point on segment DM, or line DM, and actually angle DEF will be a right angle as well. Anyways, so hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!